This special lecture series on crystal plasticity modeling. And today we are fortunate to have Professor Laszlo Toth with us. And Professor Toth holds a professor position at University of Metz in France, as well as at the University of Miskolc in Hungary. And he is very widely known in the community of mechanics of materials for more than 4 decades. He earned his high recognition through his broad knowledge in both mechanics and materials, which permits him to make the bridge between these two disciplines. And Professor Toth at the University of Metz started the laboratory LEM3, which stands for the Laboratory for Microstructures and Mechanics of Materials, in 2010, containing about 160%. And also later, he started Laboratory of Excellence of Design of Alloy Metals for Low Mass Structure, known as LabX Demos, in 2012. Professor Laszlo Toth has published more than several hundreds of research articles in peer-reviewed journal, and he has an impact factor of 51, and he is also among the top 1% of best impact scientists. And he has also conducted various international conferences, including, to name a few, the fourth European Mechanics Conference and also Shear Process Conference, and he was also the chairman of the Nano SPD6 conference and also the conference on strength of materials known as IXMA, which he conducted last year, and he is also going to host the international conference on texture of materials in the next year at Metz in France. And I would like to request Professor Daniel to welcome him by giving a memento to Professor Toth and also officially inaugurate this lecture series.
Thank you, that's fantastic.
Yeah, Suresh, please join.
Yes, please continue. Thank you. Thank you. Oh,
This is a gap which is unique to this part of the country.
oh,
So it is worn this
very,
way.
very nice. Oh, very nice. Okay. Yeah.
This is a shell of tilapia that traditionally we welcome guests by putting it on their
Oh,
bottle.
okay. Thank you. Thank you.
So now I think we will have another. Thank you.
Thanks. So I better
I
take
request
it.
Professor Daniel to say a few words and formally inaugurate this lecture series.
First of all, welcome Professor Laszlo Toth to our midst. He has just traveled all the way from France and landed at Delhi yesterday and traveled to Roorkee via Dehradun. So thank you for coming and being a part of our little workshop here, which we could organize because of your presence. And I think this is a very valuable opportunity for all students working on crystal plasticity, texture related research activity. This is a bonus that he is able to give you this hands-on experience of using the software and how to critically analyze your results. So this will, I'm sure, greatly benefit quite a number of our students, and I can see that at least 1/3 or maybe even closer to 2/5 of the PhD strength of the department is represented here. I hope others will also join because this is a one-time opportunity. But we are also lucky that if any of our students are unable to be physically present here, they are doing some experiments. We are also recording these lectures with your permission. And yeah, so that even for you, if you wanted to review the lecture again and get the fundamentals right, these will be accessible to you. So I am deeply indebted to both Professor Sumit Mishra and also Professor K.S. Suresh for jumping into it and grabbing this opportunity and dragging you to Roorkee. So we know your plan was to go to the south of India, where everybody goes, but we also are happy that we could have you here and also make this as a special opportunity for you to interact with our students. I hope that will also be pleasant for you. Thank you and wish you the best, and also for your wife, that you will have a pleasant stay in India.
Thank you. Thank you very much. Very nice welcome for me for this occasion. You see, it's not difficult to bring me to India. Actually, I think this is number 12. I am here. Starting in 1989. Previously, I was working together with R.K. Ray in McGill University. We were sharing the office for 1 year, and then we became friends. So my first trip went to Kanpur in 1989, IIT Kanpur. Well, since then he is retired. I am also emeritus professor, so a lot of time has passed. But I met other nice fellows, and then some of them, some young fellows who became my doctorate students. So I have multiple connections with India, and I appreciate very much your capacity of thinking, working, and your culture. My wife also, she is very fond of India because she's a yoga professor. So thank you very much for this further opportunity to spread some of my knowledge on material science. This is my main topic since 40 years, one can say. Although initially I wanted to become an astronomer, but I think science is very interesting on any kind of field. Actually, I held astronomy diploma as well, and physics. So you see even the first slide, which I put on here. It begins with two Indian names, yeah. So both of them, they were almost 100% my doctorate students, and then they were also in my laboratory in maths. And there is one Vietnamese and myself. Now I like to be at the end. You know, at the initial, when you start writing papers, you are supposed to be the first one. But then the best place is when you are at the end, because it shows that you are directing and helping all those people who are before you. And this is what I wish you to arrive when you become older, to reach that position, the final one, not the first one. So I'm sorry, my voice is a little bit disturbed. And that happened during the trip. Actually, I lost my voice a little bit. I wish I lost my luggage instead, but it was my, luggage is not that important, but voice is in our field is very important. Well, it's okay. I'm not going to sing. I'm just talking about science. So there will be a number of lectures, and different topics will be touched, but I was consulting Professor Suresh about what is needed here, so that we can orient it a little bit. During my research, I was dealing with quite many different subjects, so I could fit a little bit the topic to your interest as well. And so today is going to be this strain hardening simulation, fitting, and so on. At the end, you arrive to how to do it with polycrystal modeling. But we will start first some kind of empirical function, and then we will learn how to make it perfect. Actually, yes, I can say that it's going to be nearly perfect, because it is quite difficult task to reproduce what is experimentally measured, right? It is exceptional if we have some kind of agreement from our fitting or from our modeling simulation. But if the agreement is perfect, then you cannot go any further. So here, this work is will be mostly this afternoon, and then after if I have time, I will also show another strain hardening approach, which is much more known, older. But this is very new. What I show here today, you can see it is 2021, yeah, when it was published, very recently. It's coming from my laboratory. All these people were working with me at that time. And now they are all gone, actually. Anna Satyabir is still there, but he has another topic working on. So, we will jump into the topic. Strain hardening. Here is one example. That's a large strain hardening curve, which was taken on copper. And up to shear strain, you see, goes to 10 or 11, very large strain. Usually my topic is the large strain domain. So, material forming requires usually large strains. So for technical applications, technology, this is what we have to study, and we have to be able to understand all these different stages. So this was done in a torsion, which is a simple shear process, unless during torsion the bar is changing the length. And there are some length changes if you twist a bar. A small second-order effect. Here only the shear strain is shown, and shear flow stress at the outer surface. This was a bar. So this is a large strain experiment, and then you can see that one can identify up to 6 stages. But stage 1 is not there. It begins with stage 2, because I am classifying the different stages as it is done for single crystals. But in single crystals, usually you do not get to such a strain, so there are additional stages. So stage 1 is a kind of single slip stage, which in polycrystal, and this was a polycrystal, of course it is not working just at the very, very initial stage of the material, negligible. It goes into a kind of stage 2, which is a small linear stage appearing at the beginning of the deformation. You see it is not more than 0.4 shear strain. And then we get a kind of parabolic stage, which is called the stage 3. It's a nice power law, which usually describes this stage. And then finally, it is ending at it's already quite a large strain, shear strain of 1. Yeah? It's ending, and there is a new one, which is more or less linear. It's called the stage 4 of strain hardening. The characteristic of this stage that here there is a lot of grain fragmentation taking place during the process. So actually, right now I am working on a theory which is able to explain stage 4 on the basis of grain fragmentation, not on other basis. But previous theories, they are also able to reproduce that stage without considering grain fragmentation. But because grain fragmentation is happening, in that stage. And it's practically completed up to at here somewhere. It's very important to take into account. So then when this more or less linear stage is finished, then there is a transition stage up to a constant, steady state situation. And especially this stage is very fascinating because here constant stress, constant average grain size, and it goes forever. So you can just increase the strain, and the stress is not going to increase anymore, so strain hardening is finished. So this is a very characteristic behavior of all metals. Whatever, it's big CCF, CC hexagonal, these are the kind of stages what we can see. Whether the material is making dislocation cells or not, for example, stage 4 is always there. So it's quite a complex phenomenon to describe all these. Of course, there are, as we follow the history, there are, as in general, there are two ways of approaching. An engineer who doesn't really want to do modeling from the very basics, but he wants to know what is the strength of the material, he only requires a suitable curve, a function, which describes the strain hardening. He's happy with this, and then he can actually make constructions and then, buildings and so on. So that's the first stage. This is actually, it started looking into strain hardening. At first, simple fitting functions were established. And later, scientists, of course, who want to understand from the very beginning why it is so they went into modeling, simulation, and then this is what we are doing actually now. But we have to look into what is the history of this strain hardening simulation, fitting and simulation, because here as you will see as a function of time, it begins with 1909, or 1909. Ludwig and later Holloman, they were proposing this very simple function. So this is just a function which can describe, not fully, but some part, usually the initial part, and especially the stage 3. Stage 3 can be described with such kind of function. So all this is fitting, Swift, 1952, I was born in 1952. So a little bit modified, you see, by adding a constant here, basically about the same thing. And then vos, or voce, in Spanish, they say voce. We can say vos. The vos approach, 1955. It's a little bit more complex. It includes an exponential function. Yeah? And this is just a power function here. And this is exponential. And the number of parameters is increasing because here we only have 2. Here we have 3. Here we have 1, 2, 4. Yeah? No, yes. 1, 2, 3, and 4. 4 parameters. So it's getting more complicated. 4 parameters. So it's still okay. Ludwigson, 1971, has also 4 parameters. Yeah, K1, N1, K2, N2. Because this is somehow 2 different power functions put together. Instead, as you could see from the example I showed, that it's actually, the character of the function is changing. So by making such kind of 2 together, it's working better. You can reach better fitting. And then became, the basic research in which strain hardening is described with the help of dislocation densities. We know that the most responsible part of material strength of metals is dislocation density. So if there is only one general dislocation density, it's not like two phases, then dislocation density variation with strain can be described with the help of a so-called factor here, and then rho is dislocation density. It's increasing and also decreasing. So there is production of new dislocations, there is annihilation of old ones. And with this small number of parameters, actually, from here, you still have to go up from the microscopic level to go to the macroscopic one, using like Taylor factor, using the Taylor equation, which is directly relating the dislocation density to the strength of the material. And then you will get, and this is very suitable function to describe stage 3. So 1981, it was already established, even before Cox was proposing similar before. And very nice description of stage 3. And then others, like including me, with not only me, but basically there are two papers here in 1998, which is using also dislocation densities, but it's considering the cell structure of dislocations. So when dislocations, in many materials, we see that cell structures are produced. And then you can say that there are two dislocation densities. One in the cell walls, and another in between, in the cell interiors. So that modeling, what we made in 1998, is actually written in terms of differential equations for dislocation density variations in the two phases, in the dislocation cell wall and cell interior. And then making a simple composite model, one can go to the macroscopic level, and then very nice results can be obtained. Plenty of results are coming, not only the macroscopic stress strain curve you reproduce, but also dislocation density variations you get. So microstructure modeling is also possible. Here I don't show the equations, of course, this is just a list, but this became a very, very highly used modeling, 1998. And the two papers which are describing this approach got more than 1,000 citations now. So this is a very popular, well-known, but it can only be used for materials which develop dislocation cell structure. So that's a very important element. Recent new phenomenological, fitting function is Chin et al. It's a little bit similar to Vos. It's a modification of the Vos approach, you see. You find the same elements in it, except that there is a n parameter on the strain. And so it was proposed in 2004. And working quite fine, number of parameters, 1, 2, 3, 4. That's reasonable. And very recent work, Labakumar et al., so this is Indian work. It is the Ludwigson which is taken, and you see more. There are now two exponents and then one power function here. Number of parameters is increasing, 1, 2, 3, 4, 5, 6 parameters. Of course, with mathematics and more parameters, you can approach better. Of course, what we would like is to have small number of parameters, and still approaching very good. So that's the ambition here, what we have. that we would like to reach that. Now, so the work I'm going to introduce now is from Sudip Saho, who was my doctorate student, and also he was getting finally doctorate in Kharagpur. Now he's in France, and as I showed you before, the authors list. So this function, it's a little bit different from all the others, yeah, as you can see. And you can find here 4 parameters: saturation, stress, an H parameter, an A, that's already 3, and then and sigma 0,0 is the initial flow stress. So usually initial flow stress is known. You see it. You just put it into the equation. You don't have to fit. So if you don't count that, it's only 3 parameters. So from here it was 6, yeah? We go down to 3. Can we reach better agreement with half number of parameters? Actually, I will show you that yes. So this is interesting. And perhaps you also make the question, how do you get the idea to make such a function? Yeah? Well, it is not, it also has a story. It doesn't fall from the sky, actually. It doesn't come into your mind like, a vision. It has a story. So this strain hardening function, which is an analytical, empirical function for macroscopic fitting, is coming from crystal plasticity. I have been using a certain crystal plasticity strain hardening approach in my polycrystal modeling since more than 30 years. And then I was thinking whether in a similar form we can integrate it, because that's a rate equation. It's in a polycrystal simulation, you have incremental calculation. So if you can integrate that and simplify and to get something macroscopically, because in all my simulations, which I did for strain hardening with polycrystal plasticity, was very successful. I was always amazed, how come that such a modeling, which is not in the material, it's in the computer, and it is producing the same curve. I mean, exactly the same curve. It's not even different. So how is it possible? So then the idea was to make it at macroscopic level as an analytical, fitting function as well. And then once this function is fitted, the obtained parameters actually can be used as initial guess in the polycrystal simulation. Because a polycrystal plasticity simulation is much more complicated than a fitting like here. There you have quite a number of parameters, and you have to do a full, modeling, and then you plot, and you see, it's not good. I change a parameter, look at it, no good. And then you do it, during a couple of days, and with a bit of chance, you can have a good agreement. Well, I always got, but it needed quite much work. So here there is a procedure also which I propose, so that using this, a macroscopic fitting first, which is very simple. You get in a couple of minutes the result. And then the parameters you got will be very good initial guesses for your polycrystal plasticity simulation. So that's the point I'm trying to make today as the main point. Yeah, just to impress you, to show you the progress, what is happening in simulation. So in 1952, we are with Swift. This is the function we try to fit on the material. So the fitting is the broken line, And A, B, C are three different tensile test curves on an aluminum alloy. Well, the fit, you see, well, it is fitting, but not fully. There are deviations, of course. And then today, with this function, what we are proposing, it's also just fitting. Okay, you fit, you get the parameters, and this is what you obtain. So here, this is again aluminum, but in compression, tension, torsion, and then the fit is just identical. This is empirical, but then, as I said, the parameters you obtain here in a couple of minutes can be used in a polycrystal plasticity simulation. When you start the big VPSC modeling, you put everything into, you start your computer, and then you will rapidly achieve another modeling. So this is not empirical. Here you are modeling the physics, you know, crystallographic slip, strain hardening at slip system level, self and latent hardening, orientation change of crystals, all together, shape change, everything calculated. And then you still obtain a fantastic agreement with the experiment. So this is the procedure which I am proposing here. And now let's go into the presentation of this new strain hardening empirical function. I show here that crystal plasticity hardening law, which is widely used since about 30 years. And actually, I was one of them who was proposing it that long time ago. Also, there was Khalid-Indi, and we modified and so on. So that's a very suitable way to describe how like dislocation, you know, resistance to slip is increasing in a given slip system of a crystal, even the polycrystal, during plastic strain. So the parameter here is the slip rate, the shear slip rate in a slip system. Okay, what we know. We know it from, we get it from the mechanics equations, you know, by imposing the strain on the material. We can calculate, it's also complex, but that's another course, how to get the slip distribution in a crystal. It's a rate, of course, it's slip rate. There's a dot, important. And then, because there is a slip in a slip system, then there will be an increase of the resistance to slip or dislocations in another slip system, in all of them, in all which is in the same crystal. So here this is the index J, and here is the index I. There is a cross relation, self and latent hardening, we say, which is expressed with a so-called matrix. Here this QC, C means crystal plasticity. IJ, it's a matrix which is describing with coefficients what is the possible interaction between one and another slip system. So if you have like an FCC crystal with 111,110 slip, that is in each crystal 12 slip systems. So how many coefficients you have or interactions? You have 12 by 12 interactions. Yeah, how much it is? 12 by 12, 100. Yeah, too many. Yep, too many. Anyway, so this is the complexity of crystal plasticity. But we make reasonable assumptions and reduce the number of, usually it is reduced the number of these coefficients, it is Q, C, I, J, reduced to only 4, and reasonable parameters. And then, so this is the interaction. It was already proposed like this by Hill 50 years before I started to work. And then the essential part is this one here, the 3 parameters. There is the actual, at this moment, tau 0I, because this is here the dot, is the rate of change, and here this is the value. So that is known because it's like the previous state. And here we make an increment, on it, so that it's related to, so we divide with the saturation stress, so we should know that in that kind of slip system, how much it can be the so-called saturation stress. As in polycrystals, there is a saturation stress. It's similar in the single crystals as well, just the value is different. And it can be different from one slip system to the other. So that's one parameter. Another one is the power, an exponent here, which is, well, you have to find out how much it is. That's a parameter. And finally, this is the rate of hardening, H, also a parameter. And with these 3 parameters together, one can control and increase the strength of dislocation slip, and then finally get this process is able to produce in polycrystal plasticity really very, very nice agreement with experiment. So now the idea was from here. So this is a simple function, you see, rate equation introduced 30 years ago. Or even 32 or 3. So if you look at the form of this equation, this is on crystal plasticity level, But we would like to have an empirical function, empirical analytical function for fitting at the macroscopic level, like the engineer. That's what he would like. Very, very good function which is working perfectly. So then the simplification came. As you see the structure of this the same. So we drop QCIJ, too complex. 144 parameters, no good. We drop them. We keep the H, perhaps it is combined with the other. Yeah? And we keep the A with the tau sat, but now we are at the macroscopic levels, is going to be sigma, the macroscopic stress. And epsilon dot, it's replacing the shear rate in the slip system with the macroscopic shear rate of the sample. And similarly here, we replace this tau 0 with the macroscopic stress response of the whole polycrystal. So this is the idea. You see, this is how it comes, actually. And how do we go further? Well, this is not yet good because it is also a rate equation, And because this is an empirical function here, so we can try to, integrate it. But before integrating, I would like to show that this function doesn't show the strain rate sensitivity, the strain rate sensitivity effect, which is known in metal behavior, especially when you increase the temperature. Then we have M exponent, which is, so the viscoplasticity, actually. Metals are also viscoplastic, like liquids, even even in the solid state, but the M parameter is low. This is actually a constitutive equation which is relating, accounting for the strain rate sensitivity, viscoplasticity of the metals. So epsilon dot equivalent is the actual strain rate. Epsilon dot 0 is a reference strain rate at which the stress level is sigma 0. So sigma 0 and epsilon dot 0 are connected parameters. M is a strain rate sensitivity index, and then this viscoplastic power law is describing well, very well, the strain rate sensitivity of the material. So actually, our function, what we are proposing, is sigma 0. It's for this one here. And additionally, we can add the viscoplastic behavior. But the heart of the function, of course, is sigma 0, which is changing as a function of, strain if we integrate this one. So let's integrate, and then this is what we get. And now you recognize that this is the function we get. So the previous by integration leads to this analytical function. Now we have the strain, equivalent strain, as the main parameter. As a function of that, we get the stress response of the material, and we have 4 parameters: saturation stress, initial stress when the epsilon is 0. This is 0. Then we get actually that sigma 0, 0 is equal to sigma 0. So this is the yield stress of the material at 0 strain here. And there are 2 numerical parameters, the H here and the A, which is appearing at 3 different positions, you see, in this way. So that's the empirical function we found in this way. And that's what we are going to use now, and to see how it is performing on fitting macroscopic curves. Actually, sigma 0, 0, yes, it can be usually just entered here. And then we have 3 parameters to identify. Fitting a function to existing data is not a complicated business, but I still present you here a relatively simple way to do it, easy to understand, which is by minimization, which we will look into. So we have an experimental data, a number of points from I to n, number of experimental points. And we want that our function is approaching those points the best. So you have these experimental values of the stress at different strain values, and then by taking some initial parameters, you will get the simulated one from the function what you established, and then you just look at the difference, absolute value. It should be minimum, and it's approaching the best. So this is just a function what we are trying to minimize. The minimization is actually not too complex. You take not a very fancy code, but there exists also in Fortran codes which can minimize a function. But what I was doing is simply, we have 3 parameters. We have sigma sat, we have H, and A. And I initially just take an interval, the value of sigma sat. Well, perhaps we don't see it in the curve because the curve is not reaching, the experiment is not reaching the saturation stress. So it remains a parameter. But we know it is limited. So I take between 0 and let's say 1,000 megapascal. If it is aluminum, certainly it will be there. If it is a trip steel, perhaps I need to put 2,000. For the H, again, well, this is a rate of hardening, so I put up to 100,000 megapascal. Very large. And for the A exponent, between 1 and 10. Actually, 1 is not suitable. 1 and 10. And then this interval, initial interval, cut into 100 small intervals. And in each interval, at each point, calculate how much is the function value. And there are 100 for 3 parameters. 100 values, 100, 100. All combinations you calculate, you know, it's a loop, easy to do. And for each, you get a value, and then just choose the minimum one. And you already 100 times smaller approximation, you are at the right value. Then again, it's not sufficient because it's only 1% perhaps. We can go further. The new interval, we divide again into smaller ones. It's a rapid process in 1, 2, 3, certainly less than 5 iterations, you get the result. So it's like 1 minute total, the calculation. It's analytical, you know, the function. So now with computers, it's very easy. So, and then it is identified, and actually the code is available to do that on the GitHub system. Code is available, so one can try. But I will tomorrow we will do an exercise on this whole process, you know, and you will see how it is working. So the case when a exponent is 1, actually then the function becomes a linear function, as expected, which is one special case of the possibilities. And you get, of course, you need only one parameter to describe them. But we didn't check how it is working when there is strain, not hardening, but strain softening. You know, so when at high temperatures, it's possible that because of recovery processes, recrystallization and so on, it is decreasing immediately, or after a certain strain, there is a softening. So the softening is also possible to describe with this function, but by construction, this term here has to be positive in the original function. But if we make it negative, well, in that case, you know, the saturation stress is going to be actually higher than sigma 0, or lower than sigma 0, and this becomes positive. So we get a very similar function for describing softening. This has not yet tried. So those people who work for high temperature strain hardening, they could try that. I hope it is also working so good. So let's see now what results we can get by this process. So I am going to show you a couple of applications.
So basically that exponent A depends upon the shape of the hardening curve.
Yes. That describes the shape, mostly. The H is how fast is hardening. The A is the shape, and the saturation value is you know, the saturation. So it has a little bit of geometrical meaning. So here there are some results for application. Sudeep and Satya, they were working very nicely. You see all kinds of different applications in aluminium. You see each time the measured curve is with the dots, you know, and the fitted one is the continuous curve. So this is, I showed this already. Here this is for steel, for copper, again tension, and here is torsion for larger strain, because here strain is limited. You see it, tensile testing is limited, but torsion you can reach higher strains. So here we go up to now about 2 for Mises equivalent strain, and you see even for that large strain we still get perfect agreement. And then we can look into here titanium, yeah, in different directions. So it's a plate, and you can pull it in rolling direction, you can pull it in transverse direction, and then at different temperatures as well, room temperature or 300 degrees C. Each time the fitting is successful. So that's essential for the engineer, right? Are you engineer? No? Now some of you are doing thesis work here, no? I think somebody is doing a thesis is going more than engineer. Oh. Or you call them still engineer. I would call you a scientist. So we go further, yeah? So what we want, now we got this in a couple of minutes, and now we want to do modeling. So for the modeling, this is a long text. Don't read it. I just copied it from the paper. Now to go to the polycrystal simulation capacity, we have to do some kind of adjustment. We are only going to use this fitted fit function to get initial guess for the polycrystal plasticity simulation. So for that purpose, we are going to use the Taylor factor. The Taylor factor, are you familiar with Taylor factor? Put up your hand if you are, if you know what is Taylor factor. Yeah, yes. Many of you know. That belongs to crystal plasticity. I will show you what it is, but how to go from the microscopic stresses to the macroscopic ones. Basically, this is the Taylor factor. It's relating the local shear kind of values to the very macroscopic sample properties in terms of strain and also in terms of stress. This is needed because the modeling work is done with a lot of physics. So we go to the crystal level, crystallographic slip, dislocation densities, many things which are at microscopic level. But finally, by doing all this, we get macroscopic average quantities as well, and that is comparable to the experiment. And we get even, so-called orientation distribution of the crystals, which the grains, which make the polycrystal, that you can also compare with the experiment. It was measurable in experiment, and one can also follow its evolution by simulation. And if all this is agreeing, then you are doing good science, and you will get understanding. So to do that simulation work, you need a polycrystal plasticity model, which there are a couple of approaches, but the most well-known and very powerful and still doesn't need finite element calculations is the so-called VPSC model. That it stands for viscoplastic self-consistent. Viscoplastic self-consistent polycrystal modeling. I gave a course on that in Kharagpur a couple of years ago. This existing software, which is free software, one can use it. There are two versions of that, but they are based on the same approach. One is from Los Alamos National Laboratory, and the other one is from University of Metz. Because the self-consistent model is coming from Metz, actually. The basis was done there. And then two eminent researchers in Los Alamos National Laboratory, they reformulated and they made very nice software, which is working very efficiently. The Metz group, they were very good establishing the model, less good in the numerical realization of that code. I also contributed to it. And when I came, but when I came there, it was already 1992. So then the self-consistent model was proposed in 1988. So that's also existing and also very performing. And one can change, even improve the code. And this is why I was giving that course previously in Kharagpur, so that those who want to improve new physics into the modeling, they can do. If you understand the code, you can touch the code and you can change and then put new things in it. So, to go from the microscopic to the macroscopic level, we will use the Taylor factor. So in a simple procedure, we can transform our fitted macroscopic parameters into microscopic polycrystal plasticity parameters. The Taylor factor is a ratio between the macroscopic strain rate and the local shear strain rates. Here, gamma dot S is the slip rate in a crystal in a slip system. There are several slip systems in a crystal, different families even, different kinds of slips, and there are many grains. G stands for grains, so you have to make an average summation of all these, making a big average of all the shear rates, weight with the volume fraction of the grains, and make this ratio. And obviously, then this factor can transform this quantity into that one. See? Simply you put the M here, this one you put the other side, and then you have your transformation formula. That's for the strain. This is available in the code. Gamma dot S in each grain, each slip system, this is in the code. You can take it. So that's, you can calculate. The other is for the stresses, because we have two things to transform. One is the strain, the other is the stress. Strain is relatively easy like this, and this is how it is defined. And but for the stress, a little bit more tricky. For the stress transformation, we will have the macroscopic stress here, and this is the microscopic shear strength of the material, tau r, average, here. So one would think that it is just the ratio here, like for the strain. But no, not really. So this one we know here, in the simulation. And by averaging, we also know this one. So we can get the Taylor factor to transform our quantities into macroscopic one. But there is here a lambda parameter. This is new in the literature. It's so much new that it's only published a couple of. No, it's also included into that 2021. So it's just 2 years old. This parameter is a very young parameter. There are young people, young parameters, old parameters. Well, because it turns out that, this Taylor factor business is based on the energy calculation. So you calculate the energy, plastic energy, in two different ways. Grain by grain, and you add them together. That's an energy. And then you can calculate the energy in your polycrystal by multiplying the macroscopic quantities. The energy is calculated by stress multiplied with strain rate. It's a plastic power. You can calculate in two ways. And unfortunately, the VPSC model, as many models in polycrystal plasticity, is not satisfying the energy relation. It's a little bit strange. How can it be working good if it is not satisfying the basic principle of, of physics? But actually it does. But the way it is constructed and homogenizations are done, in homogenizations, many local gradients are disregarded or not counted properly. So unfortunately, the VPSC mathematical polycrystal code is lacking satisfying the so-called energy criterion. And this has to be corrected, but the correction is possible by having the small lambda parameter here. Its value is about maximum 1.3. It's larger than 1. So in a recent study, we showed that this effect is existing, and then it has to be accounted for. That's another paper. I do not present the details. It's very much theoretical. But for different testing materials, this lambda value is known now. It's published. So one can correct, actually, this Taylor factor to account for really properly for the energy relation, to correct for it. So anyway, we have the two Taylor factors, one for the strain, one for the stress. And with this helping, we can actually go to the macroscopic level, and we can also transform our parameters. Well, this I didn't know it's existing. So this lambda parameter is an analytical thing one can obtain, but it's also published, and this is the same here. Let's go for the next one. So here is the simple transformation. We have these 4 parameters here, sigma 0, 0, sigma sat, H, and A, obtained by fitting, simple fitting, efficient, fast, and precise fitting. And we want to use these values in the polycrystal plasticity code. There it is, what we need is tau 0, which is the strength of the slip systems for dislocation glide. That's the shear stress which is moving the dislocations. So it is simply going to be sigma 0, 0 divided by m. M is the Taylor factor. Here we only use the Taylor factor for stress. The saturation value is also transforming the macroscopic into the microscopic one by the m division. This rate of, here it is invented, this is H and this is HC. Anyway, I will correct that. The rate of H parameter is by m square, transforming between the fitting and what we need in the code. And the exponent is the same. Oh no, this was okay. HC and HC, yeah, it's okay. It was fine. So we have these initial parameters, and then we can do the polycrystal plasticity simulation. Now, this polycrystal plasticity simulation is quite tricky, because, as I said, it is using a very much more sophisticated hardening rule. That hardening rule, I'm going back to the initial slide, which showed how we started. This is the hardening rule we have to use in simulation, in crystal plasticity. So it has the same parameters, yes, but there is QC, IJ. These 144 coefficients. So to deal with that, since long time we have been using an approach in which this is simplified into 4 categories. So I will show you that here it is discussed. Yeah, it is discussed here. So that Q value here, there is only 4 categories. Indexed 1, indexed 2, 3, and 4. And because this is for self and latent hardening, between 2 slip systems, meaning that self-hardening because there is strain in that very slip system, very same slip system, so strength is increasing. Okay, but that slip is making dislocations which are meeting other dislocations made in other slip systems. So there is this cross effect of self-latent hardening. So that's why it's a geometrical, basically. For me, it seems to be that this big matrix, this Q, C, I, J, is a geometrical meaning, mostly. So by taking 4 groups, one group of interaction when two slip systems are coplanar. The other is when collinear. The easiest one is when it's less interaction is when it's parallel. And when it is collinear, then there can be more interactions. And when they are perpendicular, 2 slip systems, that has to be the strongest effect. And then all the other geometrical cases we put into a parameter number 4. So we only reduce to 4 parameters. And they are increasing, like the easiest one is coplanar, we put a parameter value equal to 1. For the collinear, 1.2. For the perpendicular, 1.4. And then kind of average value for all the other classes. So it's a huge simplification, but efficient and reasonable. And the testing it shows that it is actually leading to extremely good results. So that can be used in the simulation. Okay, so finally, what happens that a simple process by going from these empirical parameters to crystal plasticity initial simulation values, we can try how the polycrystal model reproduces the macroscopic stress-strain curve. If you see any deviation, you might still have to fine-tune the polycrystal model parameters. So you are permitted to change a little bit those 4 parameters which are here, and then trying the best. But the number of changes needed is very little, actually. So comparing to previous modeling efforts, when all these 4 parameters especially, all of them we had to change and we didn't have too much idea, it was really very hard. So I needed several doctorate students to do just that. No, but no. No, they are. I simplified the thing. Actually, it was the author number 2, Satyavir. He was with me, and then he wanted to do some simulation of macroscopic strain hardening curve. I said, you want to simulate texture in asymmetric rolling, okay, but we need, a strain hardening curve. Okay, so then he got a strain hardening curve in tension, fine. Then we have to first model this for tension to get the parameters, and then use those parameters in the asymmetric rolling texture simulation and all this. Okay, then I explained him how to do. So Satyavir, he started to work to fit the tensile strain curves with the VPSC model. A couple of days later, I'm asking, so it's working? He says, yeah, it's a lot of work. I still didn't get reasonable curves. Okay, just continue, it's your job. You are there for this. So then he continued. 10 days later, he still didn't get good results. He told me, Lars, so there is no simpler way for these parameters so that we can have some good initial guess. And this is how the motivation came. Okay, I'm trying to help you. And then this process was invented right after. And then we tried. And he was very happy because it was very efficient and good working. Okay, so now let's see how it is working. Oh yeah, just one more detail before I'm showing the results here. Yeah, this is about the so-called equivalent stress. You know, in mechanics, we have only two things to take care about: stress and strain. Strain can be elastic, you know, and you can readily connect it to the stress. In plastic strain, more complex, you know, it's a headache. But basically, those two things we are dealing with. Now, for the strain, there is a common agreement. It's not a big problem. We use an equivalent strain, which is a invariable quantity, you know, the von Mises strain. It's a second invariant of the strain tensor, or we usually use the strain equivalent von Mises strain rate. It's again the second invariant of the strain rate tensor. In any reference system, if you change it, is the same value. It's very comfortable. There's a common agreement on this. This is a suitable strain measure. But for the stress, how do we define the equivalent stress? The von Mises equivalent strain rate is suitable, you know, when you have different strain modes to compare. It's like we are doing a fitting in tension, and we are going to use those parameters for rolling or for torsion. So if you want to get, you know, the macroscopic response of the material in terms of stresses, for the strains we will be fine, but for the stresses we cannot do anything. We have to be, you know, we have to follow certain principles. So many people just are using the von Mises equivalent stress. This is limited. It can be only used if the material is isotropic material. So be very careful with the von Mises stress. Sorry. Strain is fine, but von Mises stress together with von Mises strain means isotropic material behavior. Okay? It's not crystal plasticity. It's very far from that. It's valid for isotropic material. It's usable. But if you are working with an isotropic case, you could just not permit it to use it. So what can be used instead? Actually, what can be used instead is the so-called work equivalent stress, work equivalent. So what's happening that epsilon dot C is, you know, is the von Mises strain rate. It's accepted, right? Now we want to define the equivalent stress scalar. You know, the problem is just this. When we do a testing, strain hardening, we are measuring scalar values, and we want to get the same scalar values from the simulation as well. But in the simulation, we see that, of course, there is strain rate tensor, there is stress tensor, nine components. So how to get one single scalar value? Well, what I am using now, and I'm proposing that everybody should do that for, you know, for the non-isotropic case, simply use the work conjugate quantity, so that you calculate here the plastic power made by the whole sample, you know, each stress and strain component, they are working here. Yeah? So this is a summation of 9 components work. Yeah? The total work. And then because we already have this one, this is the macroscopic. You know, if you multiply this with that one, on the left side you will see the same, you define the same value of the plastic power, from which you get the definition of the equivalent work conjugate equivalent stress here. It's very simple to calculate, and it gives another value. It's different from the von Mises one. It can be very much different. So when we construct this macroscopic stress strain curve, this is what we define from the simulation. The simulation has all the components. They are there. We have to account for them. And this is calculated from only that one. Okay, so that's a detail, but important. And now we look into some simulation results here. So these are the same cases what we saw before for fitting. We did for fitting empirical, without thinking, no physics, yeah, just a function, mathematics, fitting with computer, fast and surprisingly efficient, because it is describing very well the experimental curve. Now we are doing physics. Now we are doing simulation work with the VPSC model, and then the result compared again with the experiment. And this is what you see here. So it is actually almost as good as the empirical one. Very small deviations, perhaps you can discover here. They are not covering exactly each other, the curves, while the empirical one it was. But now we are doing really business, because the simulation is on the polycrystal, and you do not only get this result from the VPSC, you know. This is not the only result. It's just some part of it. With the VPSC polycrystal model, you also get, for example, grain shapes. You get the crystallographic texture, orientation distribution. And it's measurable experimentally. You can compare. That also has to agree with the experiment. So many more results are coming out. This is just one part of it. But this is one application possible of the VPSC model. So here you see for an aluminium 2024 in different tensile torsion and testing compression. And here this is the rate of hardening, you know. So the experimental, this is the derivative of the stress strain curve. This is the derivative, strain hardening rate. And this is also comparing very well between simulation and experiment. So that was aluminium, and this one is steel and copper. Well, for steel and copper now, because this is not empirical, you know, here we are doing crystal plasticity. If your initial texture, there was some initial texture in the material, like for the steel or copper, you see, which is different colors in this whole figure representation of the orientation distribution of crystals. Different colors. If it's a single color and single value, that means isotropic. Yeah, but this is not. So it's a little bit not very strong either, only 1.4 times more than the random. Here it is more, 4.2. It has a strong maximum in the 100 direction. So this is taken into account in the simulation. You discretize the initial texture into your grain orientation distribution used for the simulation, and then you introduce it in it, and then it's taken into account in this way. So here you see that's why it's added. Here the simulation results. If it is not done, actually we cannot get such a good agreement. It's also important to take into account the initial state of the material as precise as possible, which must include the orientation distribution. So again, here the strain hardening rates and the curves themselves are very, very satisfactory. And here, this is aluminum and copper. Yes, but for larger strains, here the strains, you know, these are all the cases I showed before, just for the empirical fitting. And you see that perhaps you find a little bit of deviations, you see. But look, considering the complexity of your modeling, what you are using, it is perfectly satisfactory. So that's such kind of modeling which is so successful that I hope is going to be extensively used in the future. That's the case for titanium. Titanium sheet can be very anisotropic. You see here, like usually the so-called basal poles are normal to the sheet of the titanium sheet. And even with this extremely high anisotropy, one can conveniently, you know, reproduce the results. That's for titanium, different temperature and different loading direction within the plate. Yeah. So now, of course, if you want to publish a new approach, it's very important to compare with previous ones. Once we did an excellent job. It was on twinning, you know, twinning variants and so on, very complicated. And we got a nice theory. We sent the paper to Acta Materialia, and it was refused. The reviewer said, how can you propose a new theory without comparing to the old ones? Perhaps the old ones, they produce the same. So it's very important that you not only produce something new, but you have to work on the old ones, apply the old ones, and check one after the other, you know, at least the best one, the latest one, I mean the most developed one. They have to document that this is better. So, well, we found out who was the reviewer anyway, because he was pointing out which work was mentioned, of course. I mean, of course, you mention important works, but to apply, and it's not always easy, to apply another existing theory, you have to work it out on your example, you know, you have to realize it. It's like, it's a big job. Usually people don't do, but actually the reviewer was right, that it is important. And anyway, the reviewer was John Jonas, my promoter in Canada when I started my career. Proud. John Jonas, the famous one. So we did apply that theory in which he was involved previously, and then we showed that it was working much less than our new theory. We sent the paper again. It was accepted immediately. And the author, who was a reviewer, you know, of that theory, also didn't mind that it was not working so well, because what can he do anyway? The new theories can be better than the old ones. So it's very important if you publish, don't forget to do your best. So at least one or a couple of existing theories to show how they work. Then your paper is just, you know, perfect. So here is, in this work, we did not forget about this. So comparison with other new approaches. Here you are selecting one which was a chin empirical function. You know, I presented it at the very beginning in 2004. And they were presenting curves for aluminum and copper. You see the fitting, what they could achieve. And it's just empirical, no crystal plasticity. And here, so we did the same case, we took the same. We used R function here. Here they have 4 parameters. You also have 4 parameters, but the function is different. And then we did the fitting, and there is an improvement. That's no doubt about it. So with the same parameters, we get better, same number of parameters, better agreement, and it knows even more, because you can use it in crystal plasticity simulation. Another, it's an Indian work, so it's Lava Kumar, 2021. It was just published, and then because it appeared in the same journal, we said we immediately check whether our function is as good as that one. So they made a huge work here. You see there is steel, titanium, dual-phase steel, trip, high entropy alloy, stainless steel, magnesium, all this they were doing. And pretty good agreements are obtained with their function. You see, here is the function, 1, 2, 3, 4, 6 parameters. 6. We have 4. And one of them is not really a parameter. Let's say 3, half. So we did the same and checking. And if you compare carefully one by one, for example, high entropy alloys, definitely much better. You see here deviations. And our agreement is at least as good or better. So this is, again, extremely important to in this way, these authors are happy, because their work is cited, used, and if it is working less or not, but this is another question. Science doesn't belong to you. There is only one true science. We are doing different sciences, but there is only one which is true. Okay, so, and then there is an empty page and other empty pages, because the work still should be continued here. Especially, I would be happy if somebody would try this strain softening function, which is proposed in this work. Okay, I'm going to stop here for some break. And, yeah?
Yeah, we can stop here. We can have a tea at 3:30 for 10-15 minutes.
Yeah?
And we can continue.
Yeah, okay, good. 20 minutes, yeah?
Yeah.
Okay, 20. You can make questions if you have some. But those who would like to participate tomorrow morning, in the practical, they will have plenty of questions tomorrow, I'm sure about it. Okay? Thank you for the moment.